Hello, Tensor friends. I got a good question here. How did I get Desmos to draw a tangent plane on a manifold? Okay, the manifold I'm going to use is a sphere because it's the easiest one to do. And the math in this is not very difficult. What's difficult is, like any the software, is getting Desmos to do what you want it to do. That was the tricky part of this. Okay, so I'm in desmos.com/3D. Okay, so these are the transform equations going from Cartesian, the plane. We're in 3D Cartesian space to spherical, the coordinates. Now, a Desmos is very picky about what variables you use. And you see here that I use capital X, capital Y, capital Z, because the small cap XYZ has special meaning relating to this plane, right? Okay, so for the radius, I chose the letter R because once again, R has a special meaning in Desmos. And this would normally read R sine theta cosine phi, but Greek letters in Desmos is a pain in the arse. So I just chose the T and P. So this is theta and phi. So here's the X transpose. The Y is A sine theta sine phi, and Z is just A cosine the theta. Remember, we've done this many times, okay? Now, as soon as you type in these variables, it's going to say, do you want sliders for A, T, and P? And you say, yes, I do. Okay, so now I've got theta, phi, and the radius. Okay, now you can do this in radians or degrees. I think in terms of degrees, not the radians. So stop doing that. So I chose it to be in degrees. And so you click on these things here, right? And you can change what you want. I went from 0 to 90 on the theta. I went from 0 to 360 on the phi, and the radius. I just went 0 to phi. It doesn't matter. Okay, so you pick a numbers. So I picked three numbers there. And now you can define a point using those numbers. So the point is capital X, capital Y, capital Z. Boom. Okay, there's my point. Just sticking out there. Now, here's why I used the capital letters, because these have a special meaning. So this is the equation of a sphere, and they're going to interpret that like that. Okay? So in this case, the radius is 1.6. You can change it to whatever you want. This is the phi, which swings around the equator. And this is the theta, which swings from the North Pole down. Okay? Now, putting a tangent plane on this was as simple as this. I have the transpose times X, the transpose times Y, and the transpose times Z, and all of those have to equal A squared. So it looks like that. Okay? So it was as easy as that. Like I said before, the math here isn't hard. What's hard is getting it to interpret what you want. Okay, so now that I've got that, I can start putting things on that tangent the plane, right? So I can take the derivatives of those transpose equations and find my basis vectors ER, E theta, E phi. Now, how I plot those is you don't want to plot them at the origin because it doesn't make any sense, right? You need to plot them at that point on a tangent plane because that's the whole logic of this is that you're doing this work in a tangent plane at that point, right? So you can see I started at point the P, and here's my derivative. And then now you have to add that value to the transpose, X. Otherwise, it'll put it somewhere else, okay? So it puts it there, and here's all three. So here is ER, E theta, and E phi. And now I can go up here and manipulate them and move them and the tangent plane around. And you can see them change direction, and some of them changes magnitude. All right. So that's it. I hope that helps. If it doesn't, let me know. See you later.